Averages and Variation, Chapter 3, Section 3.2. Okay. In the previous section, that is Section 3.1, we spoke about the central tendencies, that is the mean, median, and mode. Now we want to see measures of variation, that is, how far do we go, how wide is the data in comparison to the mean. You understand? Variation, measures of variation. How wide is the data spread out, or how collected, or how together the data is. Let's see what it means, okay? Now, what are the focus points? Find the range, variance, standard deviation. Compute the coefficient of variation from raw data. Why is the coefficient of variation important? The next focus point, apply Chebyshev's theorem to raw data. What does a Chebyshev interval tell us? Okay. An average is an attempt to summarize a set of data using just one number. So be it a mode or a mean or a median, you are trying to understand data using just one number. As some of our examples have shown, an average taken by itself may not always be very meaningful. All right, so just giving me one number doesn't say much about the mean income, or about the incomes of people living in my neighborhood. Say, mean is just one number, median is just one number, mode is just one number. So what does it say about the incomes of people living in my neighborhood? Say, okay, so a number by itself does not always be very meaningful. We need a statistical cross-reference that measures the spread of data. Okay, that's what measures of variation tries to address, spread of data. The range is one such measure of variation. Range is the difference between the largest and smallest values of a data distribution. So, for instance, like I'm talking about incomes in my neighborhood, right? Family incomes in my neighborhood. So it's good to say something like, oh, I don't know, the incomes in my neighborhood range from 10,000 per year to 2 millions per year. Say, I'm just making up numbers. So 10,000 to 2 million. Now that's an example of a range. You understand? So the largest minus smallest is called range. All right. Example. A large bakery regularly orders cartons of Maine blueberries. The average weight of the cartons is supposed to be 22 ounces. Okay? Weight of each carton is supposed to be 22 ounces. So random samples of cartons from 2 suppliers were weighed. The weights in ounces of the cartons were, for supplier 1, 17, 22, 22, 22, 27. Supplier 2, 17, 19, 20, 27, 27. All right. Now, range is largest minus smallest. For supplier 1, range is 10. For supplier 2, range is also 10. All right. So look, maximum minus minimum, maximum minus minimum. So that gave you the same range. Now what about the mean? Mean is what? You add these numbers and divide by 1, 2, 3, 4, 5. So add all of them, divide by 5. Likewise, add all of them, divide by 5. You get again to be 22. Okay, you can check for yourself. Add these numbers, divide by 5. Add these numbers, divide by 5. You should get mean 22. So look, range is the same, mean is the same. But as you can tell, supplier 1 has more 22s, right? So there is a mode of 22, whereas supplier 2 mode is 27. So which one is the better measure? Let's look at the two samples again. The samples have the same range and mean. How do they differ? Bakery uses 1 carton of blueberries in each blueberry muffin. It is important that the cartons be of consistent weight so that the muffins turn out right. Supplier 1 provides more cartons that have weights closer to the mean. Put in another way, the weights of cartons from supplier 1 are more clustered around the mean. Bakery might find supplier 1 more satisfactory. So I hope you understood this explanation. Let's go back. Look at supplier 1. You expect your recipe to contain 22 ounces, right, of blueberries in each muffin. Say your recipe requires 22 ounces. So supplier 1 is a better bet for you because look, their weights are closer to, more weights are closer to 22. Whereas here, look, they are far out spread out. In fact, there is nothing that's 22 ounce. Correct? So supplier 1, the data is clustered around 22, close enough to 22, most of the data. Whereas supplier 2, while the range is the same, the data is more spread out. Okay, so supplier 2 has greater variation than supplier 1. So you will go with supplier 1 because that's what you want. Less variation from the actual value you need. Okay, so the bakery might find supplier 1 more satisfactory. Variance and standard deviation. So now we can address variance and standard deviation. So we need to be able to measure. We need a measure of the distribution or spread of data. So you want to measure how much your data is spread out or the distribution of the data around an expected value. What is expected value? It is mu or x bar. There should be a line over it. Okay, x bar. So expected value is the mean. So you want to measure how wide your data is spread around x bar or mu. Variance and standard deviation provide such measures. So we are going to come up with two formulae, variance and standard deviation, which actually give you such a measure, right? Formulas and rationale for these measures are described in the next procedure display. Then examples and guided exercises show how to compute and interpret these measures. As we will see later, the formulas for variance and standard deviation differ slightly, depending on whether we are using a sample or entire population. So, variance and standard deviation, the formulae, will be slightly different based on whether you are looking at a sample or the entire population. Let's see the steps to compute sample variance and sample standard deviation. Now these steps, I'll tell you before you start working on examples, these steps are a bit longer. Okay, we will have other methods to find sample variance and standard deviation in a minute, right? Let x is your quantity, yeah, data values. So x represents data values. Find the mean. I'm looking at sample, right? Mean is denoted by x bar. It is add all the x's and divide by total number of values. This is called expected value. Okay, n is the sample size. So this is called average of the data values or what you expect to happen. All right. So for each x in your data value, take x minus the mean. So that measures how far each value from the mean. So this is the difference between what happened and what you expected to happen. This is an example of deviation. This represents deviation. I hope this is clear. For each value, you are seeing how far it is from the mean. So you take the difference. Then you square it. You square it. It probably doesn't say. You square it. If you don't square, then this sum could be 0 because the negative values will cancel the positive values. It will become 0. So you have to square it so that you have positive measure here which you are adding. So for each x, take its difference, square it and add them all up. Okay, so this is called sum of squares. Next, now sum of squares or this expression. Now here is the alternative. This expression is actually same as this value. Okay, this is easier to calculate. What is this? Sum of x squared. So take each x, square it, add. Subtract. What is this? This is a fraction. Denominator is number of guys you have upstairs. Square of sum. You understand there is parenthesis. So first add all of the guys and then square. You see the difference between this and this. Here you are adding squares of x's. Means you first square each x and then add them up. Whereas here first add all the x's and then square it. So this sum of squares is actually equal this. It takes some checking, but we won't worry about it. Just assume that this is equal to this. Now, variance. Sample variance, s squared. It's denoted by s squared. It is, you are taking all of this in the top and dividing by n minus 1. All of this in the top is same as this. So s squared is the same guy, this guy on the top over n minus 1. This is called variance. Okay, so this is the definition, but this is an easier thing to calculate. When you try problems, you will recognize this is an easier thing to calculate with. Okay, so this is called computational formula and the top is called defining formula. So this is sample variance. Okay. Deviation. What is deviation? Is denoted by s. It is square root of the variance. S is square root of s squared. All right. So the top is the defining formula. This is the computational formula. Remember what I said? You don't need x bar in here. That's why. Okay. So how do you find the deviation? Well, you have a square root of a fraction. Denominator is easy. Total number minus 1. What does this say? Add all the squares of x minus. First add all the x's and then square it. Don't forget to divide that guy by n. Okay? Okay. In statistics, the sample standard deviation and sample variance are used to describe the spread. Next example will show how to find these quantities by using the defining formula. For hand calculations, the computation formulas for s squared and s are much easier. All right. Okay. So this is the defining formula. Remember, defining formula for variance and standard deviation has x bar. That is the mean. Okay. And computational formula does not have the x bar. Instead, you have something like this. So that's the variance and that's the standard deviation. All right. So we are going to look at this example in a minute in the next video. Until then, bye.